we have a problem in uniform circular motion. Specifically, this is horizontal uniform circular motion as opposed to vertical circular motion. This is taken from problem number 58 on page 171. I encourage you before watching this video to attempt to solve the problem on your own. A race car with a mass of 615 kilograms is moving around a track. We'll say that it's in the counterclockwise direction. That's what this arrow is indicating. Our dot here represents our race car that's moving around this track. We're given the radius of the track. We're told that the radius of the track is 50.0 meters, 50.0 meters, and that it takes the race car driver 14.3 seconds to make one lap around the track. This, of course, therefore, is our period. The amount of time it takes to make one revolution is 14.3 seconds. We're told to assume that the race car moves at a constant speed, so there's no change in the speed, or the change in the speed is equal to 0, which means we're in uniform circular motion. Our velocity, of course, is still changing, however, because there is a change in direction. At this moment, our race car is pointing, our velocity vector is oriented that way, or directly up the page. By the time the race car gets here, his velocity is now oriented left of the page. His velocity has changed because the direction changed. Because his velocity has changed, then we have some acceleration, and we're asked to find that acceleration. Now we know that the direction of that acceleration is towards the center of the circle, therefore we call it centripetal acceleration. It is accelerating towards the center of the circle. Once we find the centripetal acceleration that the race car is undergoing, we'll also be asked to find what is the force that the track, or F sub t, is exerting on the car in order to keep it in this circular motion. Because if we have centripetal acceleration, there will be a centripetal force in the same direction as that centripetal acceleration that's keeping the car in the circle, because in order for its velocity to be changing, there must be some force that's causing that change in its velocity. So first we'll look at what is the centripetal acceleration that this car is undergoing. We know that centripetal acceleration, the magnitude of that acceleration, is defined by the square of the velocity divided by the radius. We're not given directly the velocity, however, we are given both the radius and the time it takes in order to make one revolution, in other words, the period. So we're going to have to use another equation to find the velocity here. To find velocity, we know that velocity is defined by change in position over change in time. For our case, since we're talking about uniform circular motion and speed, then we're concerned with distance and time. The distance around one revolution is the circumference, which is 2 pi r. There's our distance divided by the time that it takes to travel one revolution, or one circumference, and that would be period. 2 pi r divided by the period t, that gives us our velocity. We should be able to put that into our equation up here and find what the centripetal acceleration must be. Substituting this definition of velocity into our equation here, we see that the centripetal acceleration is 2 pi r over t, there's our velocity, squared, divided by, now whatever's in our denominator, r. This would give us the magnitude of our centripetal acceleration. Of course, we already know the direction of our centripetal acceleration. We take 2 times pi times our radius of 50 divided by our period of 14.3, square that value, and then divide by our radius of 50.0 meters. And we get that our centripetal acceleration is 9.65 meters per second squared. There's our centripetal acceleration. That's the acceleration of our race car. Now we need to find, well, what is the force that the track must be exerting on the car in order to generate that acceleration, or that change in velocity. I'll make a little line here to separate what's going on here. Here's all of our work to the left for centripetal acceleration. The force that the track exerts on the car is our centripetal force, right? That is our net centripetal force, okay? Again, we know the direction of that force. That's why I put these magnitude lines, these parallel bars around our net centripetal force, because we know the direction of that force is towards the center. To speak more descriptively, we would say that this is actually the frictional force between the tires and the road. We know that any net centripetal force is equal to the product of mass and velocity squared divided by the radius. mv squared over r. We've found our velocity up here. We actually found our centripetal acceleration already, so we can go immediately into a simpler version of this formula. So we could say, I know that the centripetal acceleration, magnitude of it, is m times the centripetal acceleration. We know the mass, that's 615 kilograms. We just found the centripetal acceleration as 9.65 meters per second squared. Newton's second law tells us that if we multiply mass times centripetal acceleration, or mass times acceleration generally, we should get the net force that's causing that acceleration. 615 times 9.65 with the appropriate significant figures is 5.93 times 10 to the third newtons. There is the force that's generating this centripetal motion. To summarize, we have a race car traveling in a circular track. Because it's traveling in a circle, its velocity is changing because its direction is changing. If the velocity is changing, then there's some acceleration. That acceleration is directed towards the center. To quantify that acceleration, we know that it's v squared divided by r. We're not given the velocity, but we are given the period, t, 14.3 seconds, and the radius, r, which is 50.0 meters. From this formula right here, we could find the velocity, put that into our centripetal acceleration equation. We find that our centripetal acceleration is 9.65 meters per second squared. Now we're looking at the force that caused that centripetal acceleration. That would be the frictional force between the tires and the pavement. That is the centripetal force. That centripetal force is equal to mass times acceleration. In this case, centripetal acceleration because of centripetal force, right? The force is always in the same direction as the acceleration. Our mass of our car is 615 kilograms. We just found the centripetal acceleration as 9.65 meters per second squared. Therefore, the net centripetal force, or the force that's causing this acceleration around this circle, is 5.93 times 10 to the third newtons, or 5,930 newtons. All right, thank you.